Dear students, you are welcome in this class. I am Dr. Dinesh Kumar, Principal Scientist from Division of Agronomy, IERI, New Delhi. I'm very pleased to continue this topic, evaluation of soil fertility. You already covered some aspect of this, and as you know, we evaluate or we assess the level of soil fertility for several purposes. One purpose is to see whether a soil can supply certain quantity of nutrient or not to the crop, or what will be the requirement of nutrients. Sometimes soil fertility is evaluated to see the deficiencies or toxicity and fix the limit that at this particular level of nutrient, the soil will result in toxicity to the plant. So there are many purposes of soil fertility evaluation. And learning objectives were discussed, and some glossary of difficult words was also discussed, like remote sensing, soil testing, spread meter. So process of estimating the amount of native and residual nutrient elements. Particularly in soil fertility evaluation, we want to see what is the status of nutrient. Sometimes quantitatively, sometimes qualitatively. Qualitatively, for example, if you see the visible deficiency symptoms, you can get some idea that, okay, a plant may be deficient in particular nutrient. So that is by visual deficiency or toxicity symptoms. Other is that we can analyze the plant, chemical analysis of the plant to see the status of nutrient. And in this case, critical level of nutrients are fixed for different nutrients in different crops. So we want to see whether the nutrient is at sufficient level or deficient level or toxic level by plant chemical analysis. And then we are not satisfied with the plant chemical analysis because it will just give us idea that a plant is having sufficient or deficient level of a nutrient, but it cannot guide us that what is the status of nutrients in soil and how much nutrient will be required to correct the deficiency symptom. So that is a limitation of plant chemical analysis. Then we go for soil testing or soil analysis and see the level of nutrients. And then we decide the classes that these belong to low, medium, high, and so on. But that is also sometimes does not give the correct picture. Okay, we can know the status of available nutrients, but we do not know that what proportion of these nutrients can be supplied to the crop so that it will not face deficiency. So again, we go to conduct the field experiments. And besides this, there are some microbiological approaches as well as some latest approaches of remote sensing. So objective of soil fertility evaluation is to assess the nutrient status, diagnose suspected nutrient imbalances or deficiencies, monitor effects of management on crop nutrient status, and provide basis for fertilizer recommendation. This was already covered, and you can see how these methods and tools are available for evaluation of soil fertility. Visual diagnosis, plant analysis is rapid tissue and quantitative analysis. Rapid tissue is qualitative test and total analysis is quantitative test, where we analyze exact status or concentration of nutrients in the plant system. Then soil testing or soil analysis, microbiological methods, remote sensing, and finally the best way is to have field experiments. So we are going to discuss all these. We have already covered visual plant diagnosis. So it is just indicative of nutrient deficiency or sufficiency or toxicity. Then plant chemical analysis, we analyze nutrients and see their status by rapid tissue test. I discussed about rapid tissue tests. They are very cheap, very quick, and they can be done right in the field. Only problem is that they tell you whether a plant is deficient or sufficient in a particular nutrient, but it does not tell us the exact concentration of the nutrient. Rapid tissue analysis, and I have given or suggested you test of nitrogen, similarly test of phosphorus. You need to conduct all these tests on the plant sap, and plant sap can be easily extracted. You can have pestle and mortar and take the important plant parts and crush them, and then stain them and take the sap out. And that sap can be used to see the status of nutrients. Now we come to the plant analysis, and in this we come to the total analysis of nutrients in plants. So we want to see what is the status or concentration of nutrients in plant tissues, because for every plant under different soil conditions, the critical levels of nutrients are identified. So we want to test the plant whether it is having sufficient level or less than the critical level. So for this, we need to analyze the plant samples in the lab. So in this case, there are 4 important steps you can remember. Number 1 is plant sampling. Certain guidelines are there, and then sample preparation, or it is known as processing of the sample. And then finally, you do chemical analysis and interpretation. So after analyzing the nutrient concentration, now how to interpret? Because you will get certain concentration of nutrients in different plant tissues. And once you received or got the status of nutrients, then how to interpret it, how to understand it, what is the meaning of this? Then for understanding the meaning of chemical analysis, you need to interpret it in 3 ways. Number 1 is critical concentration of nutrients, nutrient ratios, and then chlorophyll meters and leaf color chart. We can correlate our result to readings of the chlorophyll meter and leaf color chart. Now, we will start with plant sampling, processing, analysis, and interpretation. But before we move, I would like to ask you, what is critical concentration of nutrients in plants and in soils? Anybody can come forward. What is critical concentration of nutrients in soil or in plant? And also critical concentration for toxicity is also there. Does anybody know? Subrata? Subrata?
Yes, sir.
Do you know what is meaning by critical concentration of nutrients?
Sir, critical nutrient concentration is the concentration of nutrient in the soil below which plant deficiency symptoms increases, sir.
Correct. It is right. It is right. But for
decreases significantly, sir.
yeah, that is really good. But for this is good definition by you. I agree to it. But it is it can be defined in other ways also. The most common way is to define upon based upon plant growth. Plant growth. Suppose there is maximum plant growth and under a particular soil condition, and plant cannot grow more than that, or plant cannot achieve more than that yield. So that is suppose maximum yield under a particular condition. So if a plant is, if there is reduction of 10% yield, reduction of 10% yield or growth of the plant, then at this particular growth stage where you get, or in other words, where you get 90% of the maximum possible yield. So at that point of time, what is the concentration of nutrient in the plant? What is the concentration of nutrient in the soil? Will be your critical concentration. I repeat, it is the concentration of a particular nutrient in a plant at which there is 90% of the maximum growth or yield obtained by the plant or experienced by the plant, or there may be 10% reduction. And this is both way. This is for toxicity as well as for deficiency. For deficient toxicity also you have some critical concentration that it should not be more than this. Then if this particular element will become toxic. Now we move on. So first step in plant analysis is plant sampling. You need to collect a right sample. because out of whole field, suppose it is rice or wheat produces about say uh, 12 to 14 tons or more per hectare biomass. So biomass is huge, and you are taking. Also, it has to be correct representative, right representative. So plant sampling is very, very important. And sampling done of a specific plant part at a growth stage most closely associated with critical values. So what happens at a particular growth stage of the plant, the requirement of nutrient will be more. Or if the nutrient is not supplied in right amount, there will be significant reduction in the growth. So that particular growth stage is critical stage for a particular plant nutrient. Means where you get maximum requirement of the nutrient, and if any deficiency is there, then there will be maximum loss if nutrient is not supplied at that particular growth stage. So that is critical growth stage for nutrients. So sampling is done for a specific plant part and at a specific growth stage. So sometimes certain portion of the plant are more sensitive to deficiency. For example, if it is mobile nutrient, then deficiency symptoms come on lower leaves. So in case of mobile nutrient, it is better to take leaves from the lower part of the plant, or older leaves can be taken. Similarly, for non-mobile nutrient, people should prefer the top leaves or younger leaves. So that is how they decide. And within the leaf, should we take the whole leaf? Should we take the petiole? What portion of the leaf or plant should be taken? Should I sample the whole plant? Should I sample just the, so depending upon the requirement and sensitivity of the plant to a particular nutrient, we decide the plant part that should be used and the state or stage at which plant should be sampled. So the composite sample should be about 200 to 500 gram fresh weight. Sample preparation. Sample preparation is your kind of processing. So samples are at first washed with clean water and then with distilled water. There are a number of options I will discuss in practical class how to process the plant samples. But here it is mentioned that you clean with the distilled water, first with the normal water and then with the clean water. Because plant surfaces may contain a lot of dust, lot of other undesirable particle and so on. So they are required to be cleaned because those dust particles may contain certain nutrients. And then after cleaning, air dried, they are air dried because they contain high moisture. So that is to be dried before they are put in the oven. So air dried for 3-4 days and followed by oven drying at 70 degrees centigrade for at least 24 hours till you get the constant weight. So this is how samples are dried, plant samples, and we should not go beyond 80 degrees centigrade. If you go beyond 80 degrees centigrade, then some kind of thermal decomposition of the organic material may happen. It may lose some weight, it can lose some nitrogen, some sulfur. So it is advisable to dry these samples at most 80 degrees centigrade, 70 to 80 degrees centigrade. Carefully ground. Ground is grinding, making it into small pieces. Small pieces are made for homogenization. Avoid contamination while you are grinding them and mix well. So now your samples are ready, and then you go for chemical analysis. In chemical analysis, you have carbon, hydrogen, oxygen, and minerals in the plant tissues. So you need to remove carbon, hydrogen, oxygen, or you need to solubilize the elements. So for solubilization of elements, you need dry ashing or wet ashing, means by which you can bring nutrients in elemental form. So dry or wet ashing is helpful, and complete dissolution and determination of nutrients by standard analytical methods. So first you need to bring the nutrients in the form of solution, and you need to destroy the carbon, hydrogen, oxygen of the sample, plant sample. It can be done by high temperature, that is dry ashing, or it can be done by wet ashing, using certain acids to decompose it. And then this sap or extract or plant solution of nutrients is used to analyze the nutrients. And then different methods are used for chemical analysis, and results are expressed as concentration on dry matter basis, maybe in percentage, maybe in milligram per gram, microgram per gram, milligram per kg. These are different units in which we express the concentration of nutrients. Next, now you have analyzed, you have done the chemical analysis, you should go for interpretation, means what is meaning by this all. So interpretation based on the total concentration of nutrients in dry matter of plants, which are compared with standard values. The values are already given, already covered by previous research worker, and we need to compare with that critical value and grouped into supply classes. Supply classes means whether it is deficient, sufficient, or in excess. This determines whether immediate action is needed to correct the deficiency. If it is at critical concentration or lower than that, then it definitely suggests that you should have some corrective measures, like foliar spray can be done, top dressing of a nutrient can be done. So some mid-term corrections can be made if we know the critical concentration of the nutrient. So conclusions can be drawn on whether the nutrient of fertilizer applied at sowing was sufficient or should be increased for the next crop. So it can also guide us for seeing the exact or dose of the fertilizer required. Interpretation of the results. Suppose you have done chemical analysis. Now you want to know the meaning of this or interpretation of this. So there are three methods or three tools by which we can know we can have understanding of the concentration that we have analyzed. Means what is the meaning. Now, interpretation based on total analysis of nutrients or chemical analysis of nutrients in plants. So number one is critical concentration of nutrients. The nutrient concentration between deficiency and optimum supply range is the critical nutrient range. The nutrient concentration between deficiency and optimal range is the critical nutrient range. Means up to the optimal range, you have critical concentration. And beyond the optimal range also, sometimes you can have toxicity. So that will be concentration for toxicity. So CCN is your critical concentration of nutrient, is the concentration. You see this definition, what I gave you in the beginning. Critical concentration of nutrient is the concentration of a nutrient in plant that is likely to result in 90% of the maximum yields. So at 90% of the maximum yield, suppose yield is 100 tons, and at 90 ton, whatever is the concentration of nutrient in plant or soil, that is your critical concentration. If a nutrient is present below CCN, the yield or quality of crops decline. If supply of deficient nutrient increased in soil, the crop growth or yield will increase till CCN is exceeded. Now see this example, if you are able to see it. So here interpretation can be made. Suppose concentration of nitrogen was estimated in your wheat crop at 1 to 2 node stage. 1 to 2 node stage in the above ground part, you estimated concentration of nitrogen in wheat. So it is the critical concentration values are given for different crops. You can see these are for different crops, critical value of nutrients. For example, nitrogen. Nitrogen is 3%. Critical level is 3%. It is given. And at what growth stage, you can see the bottom footnote. In wheat and rice, you can see it is at 1 to 2 nodes stage. So this is the stage of the plant when it was tested for critical concentration. And then what plant part was used? It was whole shoots. Whole shoots were used and at 1 to 2 node stage, and the concentration was 3% in wheat or rice, suppose. It is the critical concentration. And your concentration was 2.5. That means your the concentration of nitrogen in wheat at 1 to 2 node stage in whole shoots is below the critical level or much below the critical level. That means the wheat plant or rice plant requires application of nitrogen. But it will not tell that how much fertilizer or how much nutrient should be applied to overcome this critical level, to reach the optimum level of nitrogen. So in this case, you can see for other nutrients like zinc, zinc critical concentration is 20 ppm or milligram per kg dry matter. And when it is at 1 to 2 nodes stage and in whole shoot. Similarly, you can check for other oil seed, for example, phosphorus concentration is 0.3 in oil seed, and in oil seed, the stage oil seed rape was there, oil seed rape pre-flowering, and you can see here. So in oil seed rape, phosphorus concentration was 0.3% at pre-flowering stage, and youngest mature leaf was taken. Youngest mature leaf was taken. So this is how you can interpret the critical concentration. Anything you want to ask? Any point in critical concentration? So you don't bother about the data or the value of these for different crop, but it is to understand what is meaning by critical concentration and how it is interpreted in this soil fertility evaluation. Now, interpretation based upon the nutrient ratios. You have already done or you have already analyzed your plant sample for different nutrients or nutrients of your interest. So one way of interpretation was CCN, critical concentration. Another way is by nutrient ratios, interpretation based upon nutrient ratios. So after analysis, nutrient ratios can assess the crop nutrient balances, because nutrients inside the plant system are in a balance, as is the case of soil. In soil, normally people say that we should have NPK 4:1 ratio of NPK. Similarly, there are certain ratio of certain nutrients are fixed or ratio of 2 or 3 nutrients where you get the maximum benefit or maximum yield. So those ratios have been identified, and this system is called Diagnosis and Recommendation Integrated System. Diagnosis and Recommendation Integrated System, DRIS. And it was introduced by Biophils 1973. So what he did, relationship between a pair of nutrients like NP, that this is the concentration of N, this is the P. Ratio will be this. So that ratio may be ideal, or that ratio may tell us deficiency or sufficiency of nutrients. So this ratio can be for P is to N, N is to K, K is to N, and so on, in place of nutrient sufficiency or nutrient critical concentration. It judges the balance of nutrients in plants, ranking the levels of nutrients in sequence, beginning with the severely deficient to highly sufficient. Determines nutrient needs of plants much before their deficiency or excess is able to reduce the growth analysis. So it has its own academic significance, but most of the time it is not being used now. However, it has its relevance, particularly in case of nutrients where you have some negative interaction of nutrients or antagonistic interaction of nutrients like phosphorus and zinc. So for them, it is important that you need to have ideal ratio of phosphorus and zinc, so that none becomes deficient and none become toxic. Particularly zinc can be toxic to the plants. Next is interpretation based upon the chlorophyll meters and leaf color chart. So chlorophyll meter or spread meter or leaf color chart, these are the simple tools which tell us, which check the greenness of the leaves. Greenness of the leaves is tested by these tools because greenness of the leaf is primarily governed by chlorophyll. If the chlorophyll levels are decreased, then plant will show yellowy. If chlorophyll levels are sufficient, plant will be green. And what is affecting chlorophyll color? It is mostly nitrogen. So nitrogen is there in the chlorophyll, which decides the greenness of the plants. And then this greenness can be known by tools like leaf color chart, spread meter, and this chlorophyll meters. So spread meter is a kind of chlorophyll meter, and you get some readings. And those readings can be correlated with nitrogen uptake or other parameters. So regular monitoring of plant nitrogen status up to the flowering can be done by these tools. Measures the leaf greenness, which is measure of the chlorophyll content in plant leaves. Soil plant analysis development chlorophyll meter is the most commonly used measure nitrogen status of plants. Spread meter is used mostly in research centers. Helps in better management of nitrogen, particularly in cereal crops like rice, wheat, and maize. So it can be employed particularly for cereals. And see the leaf color chart. It is not that much popular, but some farmers may use it. The research stations use leaf color chart, and some papers have already been published on this. This is useful tool, but still its use has to go a long way. Now, you have seen three kind of interpretations: critical concentration, nutrient ratio or trace, and then interpretation based upon chlorophyll meters and leaf color chart. But these all interpretation will tell us some qualitative idea. They will not tell us that apply so much of nutrient. They cannot tell us the quantity of nutrient to be applied. So what can tell us that what quantity of nutrient should be applied? Let us see some more soil fertility evaluation tools. So next is soil testing or analysis. So what are the objectives of soil testing or soil analysis? Accurately determine status of available nutrients in soils to give fertilizer recommendation. This is the topmost objective of soil testing, to determine the status of available nutrients in soil and to give fertilizer recommendation. Identify the deficiency or toxicity of nutrients. If there is some deficiency symptoms or toxicity symptom on the plant, then you can analyze soil and see that what is causing it. Is it excess or deficiency of some nutrients in the soil? So that can tell us, that can give us idea. To determine the chemical forms of available nutrients, you can test what is the chemical form of different nutrients. To judge general health and productivity of the soil, or simply to judge the fertility status of the soil. Because as per definition of the soil fertility, it is in general, it is the status of nutrient. So you would like to know the status of nutrient by soil testing. To estimate the response of crops to nutrients, means suppose you know the levels of different nutrients in the soil. According to that, you can apply fertilizer doses and see the response. To understand the interactions of nutrient and moisture. So variety of objectives are there for soil testing. Some background research or information is required. So soil testing requires background research on new crop varieties, because for older varieties, you already gave the recommendation. So sometimes there may be new entries or new variety may come for which you need to give some fertilizer recommendation, or some new fertilizer product has come, or some new agronomic practices have been evolved. So in those cases, you need to go for soil testing. Such research helps to determine the chemical forms of available nutrients and their mobility, most suitable extractant, general health and productivity of soils for various crops, norms for soil sampling and processing, response of crops to rates and methods of fertilizer application, the effect of season on nutrient availability, interaction of a nutrient with moisture and other nutrients. Now, what are the steps in soil testing? So, number one step, like in case of plant testing or plant chemical analysis, it is representative soil sampling and processing. First, we need to get a representative sample, then extracting the available nutrients. You need to take the nutrients in the form of solution. Like you have seen in case of plant, the acids are used, wet ashing can be done or dry ashing can be done. And here also, you need to extract the nutrient from the soil into the soil solution and into the solution so that you can do elemental analysis. And then you need to use certain chemical methods to analyze the nutrients. And then you will know the status of nutrients in soil, and you need to go for interpretation of the results. Steps in soil testing. Number one, soil sampling and processing. I hope that this group understand how soil sampling is done and what are the precautions that must be taken during sampling and processing. So the quality of soil testing depends largely on reliable sampling. Otherwise, the results, even if analytically accurate, are worthless if you are not able to take the right sample, representative sample. Your test will go in vain. The test sample, which is only about 0.00001% of the topsoil weight, very small fraction, must be representative for the whole field. Now, sampling, best time for sampling is before sowing or planting and before fertilizer application. So this is the best time. Generally after harvest of the crop, sampling should be taken. Sampling should not be done in the disturbed soil. Suppose you have harvested and you have plowed the soil, then sampling should not be taken. It should be taken when your soil is not plowed, immediately after harvest or before the plowing. Sampling should be done. So each sample should have information sheet. You need to properly label the sample, the name of the farmer, name of the field, district, date of sampling, and several other information should be written on the sample. And you can see suggested sampling procedure for a small field by Fink 1992 and for a large field. So in this is for 1 to 2 hectare, 1 hectare area. You need to take so many cores or soil samples. So like for 1 hectare, it is, you can see this pattern of sampling. So you can see it is covering almost all the parts of the field. Similarly, this pattern, zigzag pattern, it is also covering the whole field. So you can see the dots which are inside this, they can be sampled. And this is for a very large field, 15 to 16 hectare, where you need to do subsamples. So this is one particular area of the field where you are taking subsamples and subsamples from other parts of the field. So here you have taken, suppose 5 subsamples, mix them and make them one. Similarly, here also make it one, but go for 5 cores here and so on. Abnormal soil patches, areas near the fence or used for storing animal manure or crop residues should be avoided. So you need not to take from these areas, they should be abandoned. Special augers with a core diameter of 1 to 2 centimeter are convenient, but small spades can also be used. So there are a number of implements or tools with the help of which we can take the soil sample, like tube auger is there, screw auger is there, post hole auger is there, and even a spade can be used. So special augers, uniform slice of soil should be taken from top to bottom of the desired sampling depth. About 20 cores are taken from a field of 1 hectare. 20 core means sample from 20 places. So core means it is the portion of the auger. The individual cores or slices collected in clean container and mixed well. The container should be clean and it should be mixed well. Your hands should not be dirty. You can wear the gloves. From this, a final sample of about 0.5 kg or 500 gram is collected. So some techniques are available for mixing and so on. And then you take half kg. The sample should be air dried and sealed. So now you need to air dry the sample. It should not be kept in the oven for when you are using it for nutrient analysis. And then sieving can be done. Only fine soil, less than 2 millimeter, is used for analysis. The sieve size should be 2 millimeter or less. As large fields often have large variations in soil type, they must be divided into subunits of different soils. So you have seen that subsampling can be done. And then analysis for available nutrients. So we go to the next link now. Yeah, we can go to the next link. So welcome back. So after sample is taken or sample is drawn, and then you have transported it to the lab where processing of the sample was done. In processing, you need to air dry the sample, and then after air drying, you can go for analysis of the sample. So in this case, what we are doing in analysis? In analysis, we are practically, at first, we are extracting the nutrient and then testing its concentration. So the concentration of nutrient in the extracted solution are determined by standard methods. Just a minute. Concentration of nutrient in the extracted solutions are determined by standard methods. The results are expressed as nutrient concentration of air dry soil using standard units, percentage or gram per kg, milligram per 100 gram, or milligram per kg, microgram per kg, or ppm. I think you have already seen it, expressing the concentration of nutrients in plant and soil. In one of the practical class, we already discussed this. So nutrients may be indicated as element. Always they are indicated as element, not as K2O, P2O5 these days, but not oxides. So here it is important, extraction is important. You need to remove the nutrient from the soil. Sometimes, or not sometimes, most of the time, the nutrients are not there in the soil solution. They are on the exchangeable sites, and sometimes they are inside in the interlayer of clays. So you need to extract from there, which is difficult to remove them simply by water. If you take soil, if you take a certain soil and it is, you add some distilled water into it and then filter it. So some of the nutrients, very small fraction of nutrient will come to the solution, not all. So you should bring the whole quantity of the nutrient into the soil solution. So for that, you use certain extractants. Certain extractants are employed. Suppose you want to test ammonium and nitrate in the soil. Ammonium and nitrate in the soil, then what you do, the ammonium and nitrate may come partly. Nitrate can come easily into the water, but this ammonium will not come. It may be there on the interlayers of clay minerals. It may be adhered or adsorbed to the clay minerals or humus. So how to get the ammonium extracted from inside the soil particles? So for this, you can use KCl. Potassium chloride can be used, and this potassium can replace ammonium. Easily, it can replace ammonium because the ionic radius is same. So it can extract from clay layers. The nitrogen ammonium fixation is there. So ammonium that is fixed in the clays can be brought into the soil solution by potassium. So KCl is a good extractant that can extract this nutrient. Similarly, chloride can replace nitrate, because there are certain uh, positive sites on the clay colloids, and also humus. Humus and clay colloids, they also have some positive sites where nitrate or sulfate can be attached. So that can be replaced by chloride. So that is why potassium chloride is used to extract ammonium and nitrate from the soil. Similarly, there are a number of extractants that are used for purpose depending upon the nutrient. For nitrogen, water-soluble fraction, that is nitrate is most suitable, but the capacity to mobilize organic nitrogen can provide additional information. So you need nitrogen, other kind of nitrogen also. For cations like calcium, potassium, magnesium, exchangeable portion is representative. Exchangeable portion is representative of whole available fraction in most cases. So most of the time, very, very small fraction of calcium, potassium, magnesium is there in the soil solution. But most of these cations are adhered or are absorbed by the colloids. So you need some extractant. For most micronutrient cations, DTPA is used as an extractant. DTPA, diethyl diethylene triamine pentaestic acid, DTPA, now widely used as an extractant. In case of anions, the most commonly used extractant is hot water for boron. So hot water, simply by hot water, you can extract the boron because it is mostly in soil solution, number one. And number two, it is loosely attached to the colloids. And Greek's reagent for molybdenum. So some extractants are available. Students need to remember their names. For example, for nitrate and ammonium, KCl, potassium chloride is used. Potassium chloride, for example, you can see nitrate. KCl is used and calcium chloride can also be used. And most of the nitrate is in solution. It is written here, solution. Similarly, next is ammonium. KCl is the extractant, and it is both in solution as well as in cation exchange also. Means exchange sites also. It is attached to exchangeable sites also. So ammonium is both. Then H2PO4 or HPO4. Some mistake is there in this. One should be HPO4. And the extractant can be ammonium fluoride or HCl. If you are analyzing Bray, it is mostly in acidic soils. Ammonium fluoride, or what is CH3COH? What is CH3COH, students? What is the name of this? CH3COOH. Any student?
Acetic acid, sir.
Acetic acid, good. So this is acetic acid or HNO3. This is the reagent is called as malic P, again for acidic soils. So what it is doing? It will extract the phosphorus, which is fixed by iron and aluminum. Iron and aluminum P mineral solubility. So it will extract phosphorus from here, mineral solubility, you can see it. And if it is sodium bicarbonate in ocean P, phosphorus is extracted by sodium bicarbonate. So sodium bicarbonate in Olson method in neutral to alkaline soil. But here phosphorus is mostly there in calcium phosphate form, octacalcium phosphate, tricalcium phosphate, and mineral solubility. So here you solubilize it. This is the main source. And then for potassium, it is ammonium acetate, and it is mostly in cation exchange capacity, mostly part of the cation exchange capacity, or it is on the colloids. Sulfate is extracted by calcium phosphate, and calcium chloride can be used, and it is both part of the solution and part of the anion exchange capacity. AEC means anion exchange capacity because it is anion. And then zinc, iron, manganese, copper. These are metallic micronutrients. They are called as metallic micronutrients. Zinc, iron, manganese, copper. DTPA can be used. EDTA can be used, either of these. And nutrient source are zinc, iron, manganese, copper, mineral solubility. They are in mineral form. So they can be extracted from the minerals. And for boric, you see this H3BO3. H3BO3, there is no charge. It proves that boron is taken up in molecular form, not in ionic form. In many textbooks, you will find that it is tetraborate or something like that, which is not the case. It is always taken as molecular form, boron, and it can be extracted by hot water, and it is mostly in solution. Chloride, it can be easily extracted by water, and it is in solution. Now you have extracted the nutrient, and you have also done the chemical analysis. Different methods are available for chemical analysis. Titrimetric methods are available. Some spectrophotometry methods are available, and absorption spectrophotometer. Number of options are available. Instrument methods are there, titration methods are there. They can be employed to know the nutrients. Now, you have analyzed, and now you know the status of nutrients. The status of nutrient can be converted into kilogram per hectare also from different units. First, you estimate in percentage, ppm, microgram per gram, and so on. And then these can be converted into kg per hectare basis also. So what is your interpretation now? Lower the test value of the nutrient, higher is the need for external application. These are very important principles for interpretation. Lower the test value, you need to apply higher value of the nutrients. For a very high soil test value, no need to apply any nutrient. For macronutrients, the data are generally classified into three categories: low, medium, and high. But now you know 2-3 more categories have come: very low, low, medium, high, and very high. For micronutrients, a critical level is used to decide the need of the nutrient. Only you need to know the critical level. In micronutrients, there are no low, medium, high levels. There is only one level, that is critical level. So this is, you can see the interpretation of the soil test data for some nutrients in soil with medium cation exchange capacity. Soil is having medium cation exchange capacity, old data, but still relevant data from FAO 1980. So you can see available nutrient milligram per kg and expected relative yield without fertilizer. How much you can get if you are not adding fertilizer. So if phosphorus is less than 5 milligram per kg, or ppm you can say, and potassium is less than 50 and magnesium is less than 20, then relative yield will be less than 50%. If the nutrients are in the range of very low, you will get very low yields, less than 50. If again low, category of low, then 50 to 80% of the relative yield can be obtained, but still you cannot get 100% yield. If nutrients are at medium level, so at medium level you may or may not get, because range is 80 to 100. So here, if it is say 90, 95 or more than 90%, then you need not to apply any nutrient. But if it is less than 90%, then you need to apply nutrient here. You need to, of course, here you need to apply nutrients. When it is very low or low, you need to apply nutrient. But whenever it is 100, like high and very high yields, this is with respect to yield, then you need not to apply any nutrient here. So this is one kind of interpretation. Another is that suppose you analyze phosphorus and your phosphorus was 13 kgP per hectare. So you can interpret that it is in the medium range. It is in the medium range. So likewise, you can interpret your results. Interpretation of data for fertilizer requirement. This is not Indian data. This is from US, but you can see it is very interesting. The phosphorus were estimated by different methods: Bray 1, Melick 3, and Olson. There are three methods. First two methods are for acid soil, and the third one is for basic soil or neutral soil. So you can see if it is very low. So very low for Bray, it is less than 5. And for Melick, it is less than 7. The limits. And Olson has fixed at less than 3. So in this case, P recommendation is 50 to 90. And when you have low, then P recommendation is reduced 30 to 50. Instead of 50 to 90, you have 30 to 50. Then medium level, you need to apply some potash, some phosphorus, but less, much less than the low. And in high and very high level, you need not to apply any phosphorus. So the main message here is if your levels of nutrient are high or very high, then you need not to apply nutrients. You need not to give recommendation. But if it is very low or low, you must apply nutrients. In case of medium, may or may not be required. Mostly it is required. But if you are getting 100% yields by conducting some experiment from such soil, then you need not to apply any of the nutrient. Next, some microbiological methods are also available, and they are only for academic purpose people are using. So you need to remember their names and what nutrient can be used. Can they tell the deficiency? So Azotobacter plague technique used to study the phosphorus potassium status of soil. Aspergillus niger test used to determine the status of phosphorus and potassium. So both these Azotobacter plague technique and Aspergillus are related to P and K, phosphorus and potassium. Cunningham plague method used to assess the phosphorus, and carbon dioxide evolution method used mainly to judge the soil organic matter status. This is very, very important. Carbon dioxide evolution method, it studies the rate of decomposition of organic matter, or also you can say microbial activity. Microbial activity can be measured by this carbon dioxide evolution method. Next is remote sensing method, the fifth one. So up to now you have seen visual deficiency symptoms, or you have seen plant testing or plant chemical analysis, qualitative and quantitative or total elemental analysis. And at third number, what did you see at third number? Started here. So we have seen plant analysis, rapid tissue total analysis, soil testing we have seen, microbiological, one was visual diagnosis, plant analysis, soil testing, microbiological. Now we are at number 5, that is remote sensing, and after that you will see field experiments. So remote sensing is also important, particularly in today's agriculture. Now agriculture is changing very fast, and now certain advanced technologies are being tested or are being evaluated in agriculture, like your drones and drone camera or satellites. Satellites are excellent source. They are used. They are also remote sensing. They are sensing the features of the earth from far away place, and they give the data to us. So satellites have very important role in remote sensing. Remote sensing application in agriculture have advanced rapidly. Now visible and near infrared sensors. I think you know about the radiation, the spectrum, light spectrum. What are different components of it? I assume that you have fundamental knowledge of this. And then you have visible and near infrared sensors are used to detect plant stress related to nutrient, water, and pests. So we can evaluate the plant stress through the remote sensing techniques. Means we will not require to touch the plant, but we can know the certain stresses of the plant, like stresses of the nutrients, or sometimes weeds also, nutrients, weeds, water, and pests. So fundamental principle is employed here, that is when light energy, green, blue, red, and near infrared wavelength strikes a leaf surface, blue and red wavelength are absorbed by chlorophyll. Blue and red wavelengths are absorbed by chlorophyll, while green and near infrared wavelength are reflected. They are reflected from the plant surface, and reflected light is monitored by an optical sensor. So you can know that what is the input of a particular light and what is the output. Output means reflections. Is how much is absorbed and how much is reflected for both blue and red, and as well as for green and near infrared. The contrast of light reflectance. Reflectance means your mostly it is green light and your infrared, and absorption, mostly blue and red light, by leaves enables assessment of quantity and quality of vegetation. Chlorotic nitrogen stressed leaves absorb less light energy. They absorb, if it is chlorotic nitrogen stress, it is absorb less light energy. A common index used to evaluate vegetation cover is the normalized difference vegetation index. NDVI is used. It is not new, it is very old, but students should know it. Formula is NIR minus PAR divided by NIR plus PAR. NIR is your near infrared radiation, and PAR is photosynthetically active radiation. Okay, photosynthetically active radiation. Use of NDVI is based on growing plants is strongly absorbing PAR or visible light, while strongly reflecting near infrared radiation. NDVI increases, this is important, NDVI increases with increasing leaf greenness and with green leaf biomass, highly correlated with plant nitrogen status. Remote sensing of growing crops can be used to identify in-season nitrogen requirement. That is the advantage. When your crop is in the field, then you can employ this in-season nitrogen requirement. So this subject has advanced in USA, Australia. This particular subject is in very advanced form, and they use nitrogen particularly based upon this NDVI. And they employ it in precision farming because their field of farms are bigger in size, and they are using this technique to find the right time of nitrogen application. So we can know the real means in real time. In real time, we can know the status of nitrogen, whether it is sufficient or low by this technique, and we can apply the nitrogen if required. So NDVI measured at tilling is highly correlated to an uptake in wheat. So in wheat crop, NDVI measured at tilling is highly correlated to an uptake. This information is used to predict grain yield potential for purposes of estimating top dress and rates. This method, NDVI, is readily incorporated into real-time leaf reflectance guided variable top dress nitrogen application to increase yield and nitrogen use efficiency. You can understand it further with the help of this picture. This is from the Havlin book. You can see this picture, determining NDVI using optical sensor. You need to calculate NDVI of a particular vegetation of a particular field where you have a crop in the field. This is the sun giving us radiation. Radiation is there. So one case is on the left side where you have dense, you see dense dark green vegetation on the left side. Suppose you have dark green and dense vegetation and absorbs most PAR or visible light and reflect most NIR light. So you can see this. So it is 50%, you can say, or approximately 50% NIR is reflected and 50% is absorbed. If 50% is reflected, that means 50% is absorbed by the vegetation. And so far, visible is 10% is reflected. 10% visible is reflected. That means 90% is absorbed. Visible is your green blue. And then see the another case where you have very light green, yellow, and sparse vegetation. Means it is stressed. Some stress environment is there. So here you can see that near infrared is reflected just 40%. That means 60% is absorbed. And in case of visible, In case of visible, this 30% is reflected. Here it was 10%, but here it is 30% is reflected. That means 70% is absorbed. So here less visible light, that is blue and red, is absorbed, but here more is absorbed. So that is the difference in these two pictures. You try to understand it, it is very easy to understand. The dense vegetation will reflect much greater near infrared than visible radiation. Here you will have high NDVI values, whereas with the sparse vegetation reflected near infrared and visible light are similar. So now people have several models and things for ease in operation, and they have fixed certain levels of NDVI, and there are some more advanced things that are not required to understand at this stage. Now, finally, we conduct the field experiments. Field experiment, because you see soil testing. In soil testing, you can know the status of available nutrient, but many times we may not be sure that plant will still get the sufficient level of nutrient for its growth. So the best way is to conduct the field experiment. By conducting field experiment, we can know the exact requirement of the nutrients, because nutrient requirement will vary with the kind of soil. You have two different kind of soil. One is sandy soil, one is clay soil, but they are in different environments. You have tested the nutrient status of both, and you find, suppose you find that the status of nutrient is same, and then how you will give the recommendation? Will you give the recommendation of the same quantity of the fertilizer? No, you cannot give it, because you need to see the supplying capacity of those nutrients. So you need to conduct certain field experiments. Proven and effective method for assessing nutrient needs, useful for collaboration of soil test and plant analysis. So whatever data you have got from the soil test, then it can help you to work out or to calculate the nutrient recommendation. Suppose you have collected 5 soil samples, or 5 kind of soils are there in particular area. You have 5 different kind of soils. In these 5 different kind of soil, the status of phosphorus is different. Suppose in one soil it is 3 ppm, in another it is 5 ppm, in another it is 10 ppm, in other 15 ppm and 20 ppm. So phosphorus levels in your soils are 3 to say 20 ppm. 3 to 20 ppm. Then what rate of phosphorus should I apply? So what can be done? You need to conduct a field experiment with graded doses of fertilizer, because you have 3 ppm, 5 ppm, 10 ppm, 15 ppm, 20 ppm phosphorus. So you need to say that at particular level of phosphorus, what quantity of phosphorus fertilizer is giving you maximum response, and you need to find out that level. So knowing the status of nutrient in a soil will help us to get the recommendation of fertilizer by conducting field experiment. And this can be done for zinc also. Suppose your zinc levels are 1 ppm, 2 ppm, 5 ppm, 10 ppm and so, and you want to know how much zinc should I apply. So you take the soil with different levels of zinc, apply different level of fertilizer zinc, and see the response. If it is 1 ppm, how much fertilizer is required? If it is 2 ppm, how much zinc fertilizer is required to get the best response? So that is why we need to conduct some field experiment also. And sometimes we can do these field experiment blindly also. Means we need not to go for soil testing. We can straightway, based upon some idea and experience, we can use some fertilizer doses and find out the optimum dose and then develop the regression equations. So it is useful for calibration of soil test and plant analysis results, provide direct information on amount of nutrient required for a crop in a specific environment at a given yield level. What these field experiments will do? These field experiments are on fertilizer. You can do on quantity or doses of fertilizer can be tested. Source of fertilizer can be tested. and combination of fertilizer can be tested. Even time of application of fertilizer can be tested. So different variables related to fertilizer application can be tested through these experiments. However, because of the considerable expertise, efforts and cost involved, they are not suitable for individual farmer. So that is why these experiments are conducted at research station to generate recommendation of the fertilizer. Experiments carried out under field condition both at research station as well as at farmer's field. So we can make a beginning with the greenhouse experiment on nutrient management or rate of application in pots, but that will not compensate or that will not be equivalent to the experiment conducted in the field. Because in field soil profile is different, the depth of the soil is different, the movement of water is different than the pots. Therefore, pots can be used only to see whether nutrients are deficient or deficiency symptom of nutrient can be studied in pots. But field experiments are required to evaluate response of fertilizer. Two kind of experiments are there: control test plot and complex experiment. Control test plot, here you need to compare two things. One is control, other is fertilizer rate. Suppose you want to show to the farmer that nitrogen application increases yield. So you take 120 kg nitrogen in one plot, in another plot you do not apply, and show to the farmer, see the response of nitrogen. That is your control plot where you have just a single variable. And in complex experiment, you have two or more variables. Zinc and phosphorus level, zinc, phosphorus, and sulfur levels can be tested together. So that is your complex experiment. So control plot, I have already told you, it is just one treatment is taken and it is kind of demonstration to the farmer. So used to determine whether a particular nutrient is likely to be deficient or not. To determine the need for sulfur, the strip fertilized with NPK plus sulfur, while the remaining area means you can have two strips. In one you have NPK plus sulfur, in another you may not have sulfur. So now you can show the response of the sulfur to the farmer. So this is also a kind of control test plot. So here control does not mean don't apply any nutrient. So sometimes it can be zero, but sometimes here the sulfur is the control. Means sulfur is not applied in one, in another it is applied. So therefore sulfur is the control here. By comparing the color, growth and yield of the crop in the selected strip and the remaining field, a conclusion can be made about the changes required in existing fertilizer practices. Control plot. This can be quite convincing as it is carried on the farm. Now see, complex fertilizer experiments or complex experiment studies of nutrient needs to increasing nutrient rates. Means you can take several levels of nutrient. I think if you remember, I taught you this regression equations, correlation regression in last course. So you can just refresh. And there we have taken different doses of the fertilizer and seen or nutrient and seen the response. And then you can develop the equations and that can suggest you the optimum rate of fertilizer application. If the quadratic equation is significant by employing the F test, because you will have different levels of fertilizer and response, the yield at one particular level of fertilizer, you can plot the equation, make the regression equation and fit the quadratic equation actually. And if it is significant, by F test, go for method of least square to fit the equation. And once the equation is fitted, you can work out the optimum dose of the fertilizer. So this completes this part, that is your soil fertility evaluation. So your questions are welcome.